So today we're going to do both looking at the slope-intercept form of a line and use it in applications on some scatter plots. So I'm going to start off with this graph y equals 3x plus 2. This equation y equals 3x plus 2. We're going to graph it. Same thing that we did last time, use a table of values to go ahead and plot some points. So I've got x and y, and come up with a bunch of values of x, a couple of negative ones, a 0, and a couple of positive ones in here. Ones that fit in well. This one's really easy because there's no fractions. Plug them in here. 3 times minus 2 is negative 6. Plus 2 is negative 4 is my y value. So y equals to all this. Y is equal to plug negative 1 in for x. 3 times negative 1 is negative 3. Plus 2 is negative 1. 3 times 0 plus 2 is 2. 3 times 1 is 3. Plus 2 is 5. 3 times 2 is 6 plus 2, which is 8. So here's some points that some of which will fit on my graph here. X is negative 2, y is negative 4. That's negative 2 to the left and 4 down. Or sorry, 2 to the left and 4 down. So I go 2 left and 4 down. There's my point right there. X is negative 2, y is negative 4. Negative 1, negative 1. Right there. 0, 2. We have x value of 0, y value of 2, x value of 1, y value of 5, and then the last one's off my graph. So anyway, I've got a straight line here. I can simply connect the dots, and I have my line. All right. Let's do it. Okay. Let's try the same thing on this other graph over here. Y equals 1/4 x plus a negative 1. This time I'm going to use values of x that are divisible by 4 since I'm taking 1/4 of x. So I'll try 0 is always a good one. I've got 4. I've got negative 4. Those are probably some good points to start off with. Other points that are divisible by 4 would be like 8 and negative 8, although those won't fit into my graph. All right, so x is 0 plus negative 1 is negative 1. X is 4. 1/4 of 4 is 1 plus negative 1 is 0. A negative 4, a fourth of that is negative 1 plus another negative 1 is a negative 2. All right, the other ones don't even fit, so I'm not even going to put them in there. So I've got 3 points anyway that I need. That's the minimum I need to really check to make sure I have a straight line here. And I've got x is 0, y is negative 1, x is 4, y is 0, and x is negative 4, y is negative 2. All right. All on a straight line there. Connect them. Okay. All right. Well, actually, I should keep this in the graph. Didn't realize it was off the graph there. All right. Keep it neat. Keep it on the graph. Okay. So now I have 2 lines. So let's find the slope and the y-intercept of each of these. So I go back to the first one. What's my slope? Well, from any point, I'm going to go. Slope is rise over run. I'm just going to write that in there to remember it. I'm going to rise 1, 2, 3, run 1. So that's a rise of 3 and a run of 1. Both of those are positive numbers. 1, 2, 3 positive and 1 positive. I could also go from this point and go backwards and go down 3. 1, 2, 3. That's negative 3 over a negative 1. That's also that gives you the same answer, which is a slope of 3 over 1 or 3. All right. My y-intercept, where does it cross the y-axis? Right here at 2, so the y-intercept is 2. All right, what's the slope? All right, look at this one here. This one rises 1 and a run of 1, 2, 3, 4. It's a rise of 1 over 4. Or sorry, rise over run of 1 over 4. All right, and same thing from here. I could go 1 and 1, 2, 3, 4. Okay, the y-intercept right here is at negative 1. Okay. So here's the big question now. This is where we're going to learn something new. Looking back at both of these problems, how do the equations y equals 3x plus 2 compared to a slope of 3 and a y-intercept of 2? Where do we see these numbers here in the equation? Hey, look at this. The 2, the y-intercept is right there, that number right there in the equation. And the slope, that 3, that is right there in the equation? No, that can't be. Wait, let's check it, see if that works on this one. The slope here, we say is 1/4 looking. Oh, that is also the number in front of the x, is the slope. And the y-intercept minus 1, that's the number by itself that's not multiplied by the x. the constant term there. So the constant term is the y-intercept, and the slope is the coefficient of the x term, the number being multiplied by the x. Interesting, okay? Okay, so the coefficient of the x term is the slope, and the constant term without an x is the y-intercept. So that means if I'm looking at this equation, y equals 4x minus 2, and they ask me for the slope and the y-intercept, the slope is the coefficient of the x term, which is 4, so slope is equal to 4, and the y-intercept is equal to the constant term, now including its sign, so that is a negative 2. So this number 5, this next problem is actually probably the one type of thing on the test that more kids get wrong than anything else. And part of it is because they forget that everything that we just learned is sort of a cheating method of figuring out what the slope and the y-intercept are. And in order for this cheating method to work, everything's got to be in the correct format. For instance, when I look back at this original one, notice that this is y equals to 3x plus 2. We have the y is by itself, then we have the coefficient of the x term, and then we have the y-intercept. It's written, this is actually called slope-intercept form. But notice that the y has to be by itself for it to be in slope-intercept form. Okay, when I look at this next one, number 5, this one is not in slope-intercept form. The x term is on the same side as the y, and the y needs to be by itself. So how do I get y by itself? First I have to subtract x from both sides since y has x added to it. So I subtract x from both sides. And now I'm going to be left with y on this side, which is what I want. And I could write y equals 6 minus x, or minus, I prefer it to put the x term first, because that's what slope-intercept has the x term first, and then the y-intercept after that, minus x plus 6. So again, 6 minus x is the same thing as minus x plus 6. It's important to understand that this is it's a negative x and it's a positive 6. It doesn't matter what the order of them is. All right, so now I'm ready to explain what the slope and the y-intercept. Now it's in slope-intercept form. The slope is the coefficient of the x term, which in this case is now a minus 1. That's minus x is the same thing as minus 1x. So my slope is equal to minus 1. And my y-intercept is the constant term here, which is 6. So looking at this next one, I have the equation y equals negative 3/2 x minus 1, and I want to graph that. Well, I know that my slope is negative 3 over 2, the coefficient of the x term, so I write that down, and my y-intercept is the constant term, the minus 1. All right. In order to start off the y-intercept of minus 1, I want to start with my y-intercept because I can't use my slope until I have a certain point to start with. This tells me how I could move from that point, but the y-intercept, it tells me which point to start with. So the y-intercept is minus 1. That means I'm going to put a dot right here on minus 1, and now I have somewhere to start. Now the slope of minus 3/2, a lot of people struggle with that negative. Which negative is that? Is that the negative on the top, negative on the bottom, or the negative on both of them? Well, it could be either the top or the bottom. So in other words, negative divided by a positive is a negative, or a positive divided by a negative is also negative, but it can't be a negative divided by a negative. That actually will give me a positive, so that can't be. So I'm going to start off with this one here. I'm going to go, again, this is rise over 1, so I'm going to rise minus 3, which means I'm going to go down 3, 1, 2, 3, and I'm going to run a positive 2, 1, 2. So that gives me a point right there. Okay? I could alternatively go the other direction and do a rise of positive 3 and a run of minus 2. So a rise of positive 3 goes 1, 2, 3, and a run of negative 2 means go to the left 2, 1, 2. Notice that all of those points are on the same line. It doesn't matter which one of those. In fact, it's good to do both of them so that I have more points to connect. I can't go down 3 and right 2 over here, but I can go up 3 and left 2 and to get some more points over here. All right, it's always good to have more points on there to draw my graph. Then I put in my line here. And now I have graphed that equation. Okay, on this next one, the student council wants to buy posters advertising the school's carnival. The design shop charges $15 to prepare the design. That's just a fixed cost. And so that's just a constant number that's not going to change. Oh, constant, that must be the constant term. And then they're going to also charge $3 for each poster printed. So $3 for one poster is 3 times 1, $3 for 2 posters is 3 times 2, $3 for X posters is 3 times X. So the total cost Y can be represented by the equation Y equals to 3 times X plus 15, where X represents the number of posters. So they're going to ask us to graph it here. So I have Y equals to 3X plus 15. I start off with my Y-intercept, which is 15. And I go up here on the y-axis. I have 0, 0 right here. Normally I've got some negative numbers in here, but there's not going to be any negatives on this graph. I go up to the y-intercept 12, 15 is right here. And then I have a slope of 3 over 1. Now this one's a little bit tricky. Slope equals to 3 over 1. Okay. So I'm going to have to rise 3 and run 1. But actually, I've got to be careful about my scale. Are all these boxes, each of these little squares represents, let's see, 3 on the horizontal one, right? We go 3, 3, 3, yeah. And the vertical, sorry, that was the vertical one. The horizontal one, 3, 6, 9. So yeah, these are also 3. So they're each worth 3. So going up 3 and over 1, I could either, and this is kind of challenging, go up 3 and then over like 1/3 of a square because that's 1. Or since since everything is worth 3, it's basically, I could think of that if I multiply this both by 3 over 3, I'm going to end up with 9 over 3. 3 over 1 and 9 over 3 is the same ratio, so I can go up 9 over 3. So up 9 is actually going up 3 squares, 1, 2, 3, and over 1. So really, I'm still going up 3 over 1. The scale makes this a little bit more confusing that way, but I'm going up 9 over 3 or 3 over 1 is the same thing. Up 3 over 1, up 3 over 1, up 3 over 1. All right, all the way here. So now, there's my line. I have my graph. I just got to connect the dots here. Okay. All right, use this graph to find the cost for 15 posters. All right, so down here, I've got, this is posters. Down here, I should have put the scale in here before, or the labels here. This was posters. And this was cost right here. Find the cost for 15 posters. All right, so 15 is right here. Look at the number 15 all the way up until I hit right here, and that hits right at 60. So the cost for 60 posters is, 15 posters is $60. What does the slope represent here? And what does the $3 represent? Well, it costs $3 for each poster printed. So it's there's a couple ways we could answer this question. Slope equals to rise over run. And in this case, we're going to rise $3 for every one poster. And that's my slope. It actually means $3 per one poster. All right. What does the y-intercept represent? The 15. All right. That is the fixed cost of $15 for the design. Okay. Okay, so now we're going to do the same kind of problem here, but starting off first with a scatter plot of some data. So I want to be able to graph this data, and this is comparing the water depth to the temperature. All right. And in this case, the temperature is a function of the water depth. Usually you can basically look at this table. The one on top should be our x-axis one. So I'm going to put the water depth here on the bottom. And the temperature in degrees Fahrenheit is going to be my vertical scale. Water depth is in feet in here. Okay. Now my water depth goes from 0 up to 50. So I'm going to, this case is a good chance to start at 0. I go up to 50. So I want to be able to use at least half of my graph when I'm doing it. That's a good rule of thumb. I'm going by nice numbers that are easy to use, like 10s are good, but if I did every 10 here, I'm not going to be using half of my graph. So if I use 10 for every 2 squares, I'm actually going to be using a little more than half of my graph, which is good. If I were to do it every 3 squares, it actually, sometimes using 3 squares as an odd number doesn't make the graph any better. All right, so at temperature, degrees Fahrenheit, looking at this one now, looks at my lowest temperature is 50, my highest temperatures, lowest temperature is 53, highest temperature is 74, but I like to leave a little bit room on either side, so maybe 40, if I go by fives, I can go from 45 to 75 or 80. So if I start off with 45, let's see if this works. 50, 55, 60, 65, 70, 75, 80. I don't really necessarily need any more room there. Okay. Now I'm just going to plot the points. A water depth of 0 gives me a temperature of 74. A water depth of 10 gives me a temperature of 72. Okay. A water depth of 20 feet gives me a temperature of 71 degrees. 25 gives me 64. And I'll let you go ahead and finish that off and compare it to mine here. So once I have all the scatter plot points on there, we're going to try to draw a line of best fit that best fits this data. Now, if you notice, my points are not in a perfectly straight line, but I'm going to try to approximate it. All right. And some of my students have a lot of trouble drawing a good line. All right. So I'm going to start off with showing you what would be some bad lines. Okay. So if I were to put my ruler underneath all of this data, you can see that all of these points are above my ruler, and that would not be a good one to use because it's not really putting them through the middle of these points. Also, same thing if I put them above it too high here, I've got all my points underneath and it doesn't really put me through like the middle of those points. I'm looking for something sort of more in the middle. The other thing some of my students do is sometimes they try to kind of go straight across here, and you notice like on the left hand side I've got points above it, and on the right hand side I've got points below my line. All right, that means that I haven't turned my ruler enough to sort of put them so that they're kind of going through the middle. Same thing if I did it this way, I'd have too much this way. I have a whole bunch of points above my line on the right and below my line on the left. That means that I haven't turned my ruler to follow the points as much. So I'm not trying to hit all the points. I'm just trying to get as many as I can and have a good line that goes through them. So then I'm going to draw a line that connects those. All right. There's certainly a lot of ways. You can see that most of my points are not very far away from my line. Many of them are almost touching. They're all pretty close, and so that's a pretty good line in there. Not the only one that you could draw, because there are computers that can have a computer way of doing that, but by hand, they're going to be slightly different. Your equation might be slightly different than mine because of it. Okay, so now I'm going to answer a few questions. Does the data have a positive or a negative relationship? Well, as the water depth goes up, the temperature goes down. So that is a negative relationship. One goes up, the other goes down. So now we're going to write an equation of this best fit line. Okay, so we know that it's going to have a negative relationship. That actually means it's going to be a negative slope. So we need to remember that. We better check at the end to make sure that it has a negative slope. Okay, best fit line. So the first thing I want to look for is my y-intercept. Okay, so here's my x-axis, my y-axis goes straight up here, and follow up my y-axis until I get to my y-intercept, which is right here. Not at this point here. I'm not actually looking at my points anymore. When I go to find an equation of that line, I am ignoring all of my data now. I don't have to pay any attention to that. I'm only looking at points on the line, not at points on my graph anymore, or these data points, I should say. So I'm going to look at this point right here. That actually looks like I have a y-intercept of 80. Yours might be slightly different than that. That's fine. So I'm going to draw in an equation of best fit line. I know that we're going to have y equals to something x, and then my y-intercept is plus 80. There's my constant term right there. Now the only thing I have left to do is find the slope. That's the cool thing about finding this best fit line. There's only two things I need to find, the y-intercept and the slope. All right, so now the slope. All right, this one's a little bit challenging. I do already have one point here. I know that the graph goes through the point 0, 80. All right, I need to find another point. All right, and I usually try to find a point if I'm using one way over to the left, I want to find one way over to the right. And I'm going to look at this point right here. and that has a point of 50. And I like it when it comes at the crosshairs, but I didn't use one on the crosshairs. I don't see, besides this point where it comes right at crosshairs. But I'm going to use this point way over here, 40, and it looks like I'm around about 49 there, at 50, 49. So those are, I now have 2 points, and we already know how to find the slope of the line that contains 2 points. We do the rise over the run. So I'm going to do this up here. I'm going to do rise over run. The rise is the difference between their two y values. I rose from 49 to 80, or actually going from this point, it goes from 80 down to 49. So I'm going to do rise of, let's go ahead and do the second point, 49 minus 80. And the run, if I'm going to do 49 minus 80, I better do the run in the same direction, 50 minus 0. All right, and 49 minus 80, let's see, do that in head. 50 minus 80 is negative 30. One more makes that negative 31 over 50 minus 0 is 50. There is my slope, negative 31 over 50. We said it was a negative, so I definitely want to make sure that's a negative number. It is. Good. So I got y equals to negative 31 over 50x plus 80. That's the best fit line. Now, once we have that equation, we can use it to predict the temperature at a depth of 55 feet, for instance, somewhere down here. We could use our graph here and be able to predict it there too. 55 feet's right here. That looks like it's going to be about 46, 47 degrees. But we can also use it in our equation, and that's what I want us to, it says use the equation to do it. So I'm going to plug in here, y, which is my temperature, is equal to negative 31 over 50 times x, and x in this case here is the depth, which is 55 feet. So I'm going to plug in 55 there, plus 80. All right, I'm going to pull out my calculator here, and I'm going to multiply negative 31 divided by 50 times 55 plus 80, and I get 45.9. So my temperature is equal to 45.9 degrees. All right, so 45.9 degrees Fahrenheit.